Hello everyone, and welcome to my video about the Schrödinger equation. In this video, we're going to explore where the Schrödinger equation comes from, why matter behaves like a wave, how we can motivate the equation step by step, and what its probabilistic interpretation really means. By the end, you will understand not just the formula itself, but the ideas that make quantum mechanics possible. Let us now start with an introduction. Before quantum mechanics truly existed as a theory, one thing was already well established: the wave particle duality of light. Light creates interference patterns like a wave, yet it arrives in discrete packets, so called photons. Louis de Broglie then took a bold step in his PhD thesis. He extended this duality to all matter. He proposed that every particle has a wavelength. Lambda equals h divided by p, where h is Planck's constant and p is the momentum. Only a few years later, in 1927, this was dramatically confirmed. Davison and Germo observed electron interference, direct proof that even electrons behave like waves. So if matter behaves like a wave, then there must be a wave equation that describes what this matter wave looks like and how it evolves. And that's exactly what we're going to motivate now. The Schrödinger equation cannot be derived at all. It can only be motivated. So let's start now by looking at a simple plane wave. Psi of x and t equals a times the exponential function of I times kx minus omega t, where a is the amplitude of the wave. This is useful to study its derivatives. So now let's look at the derivatives. First, let's start with the second derivative in space. So the first derivative of psi is ik psi x of t and t. When we do it the second time, so the second derivative of psi equals minus k squared times the function itself. Let us now use the de Broglie relation where p equals h bar times k. Let us square it on both sides and rearrange it a bit so that k squared equals p squared divided by h bar squared. Let us now insert this into the equation above and also multiply both sides by minus h bar squared divided by 2m. This is the result we are getting. On the right hand side we can see p squared divided by 2m. This, in classical physics, is nothing but the kinetic energy. And as we know, the kinetic energy is the entire energy minus the potential energy. And in our case, the potential energy is just the potential. Let us plug it into the equation once again, and we get the equation. E psi equals minus h bar squared divided by 2m, the second derivative of psi, plus the potential times psi. Now let's focus on the time derivative. If we derive psi, we get minus I omega times the wave function. Once again, we use a relation which is E equals h bar times omega. Let's insert this in the equation above and rearrange it a bit. So we get I times h bar times the first derivative for time of psi equals h bar omega times psi, which is E times psi. So now we got both equations, the second derivative in space and the second derivative in time. And we can see that both equations give us the total energy. So what we can do now is just insert E times psi of the one equation into the other. And in the end, we get the time-dependent Schrödinger equation, which is I times h bar, the first derivative of psi in time, equals minus h bar squared divided by 2m, the second derivative of psi in space plus the potential times psi. And this is the time-dependent Schrödinger equation, the wave equation for matter. Now comes an important step. If the potential is time independent, which means v is only v of x and not of t, then the Schrödinger equation can be separated into a space part and a time part. We use the product approach. Psi of x and t is phi of x times t of t. We plug this into the Schrödinger equation and divide it by psi times t. We get I times h bar times 1 divided by t dt h bar squared divided by 2m 1 divided by phi and the second derivative of phi in space plus v of x. The left side now depends only on time, the right side only on space. This can only be true if both sides equal a constant, which we call E, the energy. Thus, I times h bar times 1 divided by t dt equals E, and also minus h bar squared divided by 2m, second derivative of phi in space, plus v of phi equals E of phi. Let us now solve the time part. We know that I times h bar 1 divided by t dt equals E. We can rearrange it so that we have dt equals minus I e divided by h bar times t. The solution for that equation up there is very straightforward and easy. I will just give you the solution, which is t of time equals the exponential function of minus e times the energy times the time divided by h bar. The constant factor in front of the exponential function is just put into phi of x. So if the potential is time independent, the wave function has a simple phase dependence, which is psi of x and t equals phi of x times the exponential function of minus e times the energy times time divided by h bar. The space part then obviously satisfies minus h bar squared divided by 2m times the second derivative of psi in regards to space plus v of x times psi of x equals the energy times psi of x. This is the time independent or so-called stationary Schrödinger equation. Because the absolute value of psi squared equals the absolute value of phi squared times the absolute value of the exponential term squared, where, as you know, if we square the absolute value of an exponential function which is imaginary, then we get 1. Therefore, the solution to that is just the absolute value of phi squared. So the probability distribution does not depend on time. This is why we call them stationary states. So psi is not a physical wave like water and sound. We detect individual particles single clicks on a detector. So what does this tell us then? Max Born therefore proposed that not psi itself is physical, but its modulus squared. So the probability of x and t equals the absolute value of psi of x and t squared. And crucially, the absolute value of psi squared is the complex conjugate of psi times psi. The wave function times its complex conjugate. This guarantees that the probability is real and positive. This explains both why particles appear one by one, but yet their distribution shows interference patterns. Let us now quickly talk about the key properties of the Schrödinger equation, the first one being linearity. If psi1 and psi2 are solution, so is A times psi1 plus B times psi2. This is the basis of interference and superposition. The Schrödinger equation is non-relativistic. It's only valid when speeds are much smaller than the speed of light. If this is not the case, we would need the Dirac equation. Also, probability is conserved. If we integrate the absolute value of psi squared over the entire plane, we obviously get 1, because the particle, or let's say the wave, has to be somewhere. So finding it somewhere within the space is always 100%. Also, phase matters only relatively. Absolute phase is irrelevant. Phase difference, however, cause interference. In conclusion, the Schrödinger equation is the fundamental equation of quantum mechanics. It does not describe the path of a particle, but the evolution of the probability amplitudes for where it might be. Starting from wave-particle duality and de Broglie's idea of matter waves, the Schrödinger equation becomes the law that governs the dynamics of those waves. I really hope I was able to help you with this video. If you have any questions, feel free to leave them in the comments, and until then, we will see each other in the next video.